Good morning to everybody. Our work concerns turbulent transport in Tokamak-plasma throughout a thermodynamic approach. This work has been accomplished in collaboration with Philippe Peters, Pasquale Nardone, and Enrique Tirapeghi, late Enrique Tirapeghi. The work is organized as follows. In the first part, I shall explain very briefly what is a tokamak. Successively, I will explain three significant tokamaks reactors: ITER, DTT, and FTU. I shall explain what is the problem to be solved, and I will speak about the transport processes in tokamak-plasma when plasma is subject only to thermodynamic forces, thermal and pressure gradients. After this, we shall solve the partial differential equations that have to be satisfied by transport coefficients for a plasma subject to these two thermodynamic forces. Two regimes will be analyzed in details: collisional regimes, plasma in collisional regimes, and plasma, tokamak plasma, in turbulent regimes. Finally, we shall show the fair agreement between experimental data for the Frascati-Tokamak upgrade and theoretical prediction. What is a tokamak? Tokamak, it is a device, a toroidal device, where plasma is very hot. Plasma is composed by deuterium and tritium, very hot. This means that electrons are separated by nuclei. Plasma is confined thanks to magnetic fields. And in this particular case, two components of the magnetic fields are necessary for confine and stabilize the plasma. A toroidal component that can be seen on the right, top right of these slides, and a poloidal magnetic fields. We can see the coils on the left. Here I show the parameters of ITER. ITER, the International Thermonuclear Experimental Reactor, which is the biggest reactor under construction in Europe, in Cadarache, France. As you can see on the left, the circle, the red circle, give the proportion between a human person, the size, having the size of the diameter of this circle, and with respect to the size of the machine. Indeed, the major radius of the ITER is about 6 meters. The minor radius is 2 meters. The toroidal fields is 5 Tesla, and the plasma current is 15 megampere. The thermonuclear reaction in ITER is obtained throughout a collision between deuterium and tritium. Deuterium made by one proton and one neutron. You can see the scheme on the top right of the slides, while the tritium is composed by 2 neutrons and 1 proton. After collision, we have helium-4 and a neutron. The total mass of the reactions, neutron plus helium-4, is less than the mass of initial component, deuterium and tritium, due to the celebrated Einstein relations, and the difference is in the form of kinetic energy. The kinetic energy is the gain of the reaction. So ITER converts the kinetic energy in energy to be used for producing electricity. Here I show you another tokamak, the divertor tokamak test facilities, which is under construction in Frascati, Rome, Italy. This is a tokamak, not a reactor, in the sense that there is no reaction deuterium and tritium. But the main goal of this tokamak is to test the different devices that will be composed the AMO, the next generation after ITER, the divertor. Divertor is a device that within a tokamak and a accelerator that allows the online removal of a waste material from plasma while the reactor is still operating. In brief, the DTT, divertor tokamak test facilities, is a sort of a preliminary example in order to study the problem that will be faced by big reactors and to solve this problem. The simplest tokamak in the world, I would say, is the Frascati tokamak upgrade, called FTU. This particular tokamak, which is not a reactor in the sense that even in this case, in the tokamak, we shall not nuclear reaction DT will not occur, but is the simplest, I would say, tokamak, because it is a very small tokamak. The major radius is just about 1 meter. The minor radius is 30 centimeters. But the plasma is subject to a toroidal field very, very strong, 8 Tesla. This is very important, as in this case, turbulence exists but is quite low, and then can be studied analytically and theoretically. This is the reason why we decided to study plasma confined in this tokamak and then compare the theoretical results with the experimental data obtained in FTU plasma. What is the problem? The problem is that currently there is a big discrepancy between theory and experiments. In the figures on the right, the highest behavior represents the experimental data. It represents the electron losses. The energy loss, electron energy losses towards the boundary. And the other course on the bottom is the theoretical prediction. As you can see, there is a strong discrepancy both qualitatively and quantitatively between experimental data and theoretical prediction. In this case, the discrepancy in magnitude, the order of magnitude of the discrepancies amount about 1000. But in JET, the other reactor located in Calais, England, the discrepancy is 10,000. So the aim of this work is to set up a theory able to obtain an agreement within experimental data and theory, both qualitatively and quantitatively. So, we start by writing the entropy production of the plasma. We suppose that the plasma is driven out of equilibrium due to two thermodynamic forces, the thermal gradient and the pressure gradient, indicated by x1 and x2. J1 and J2 are the conjugate fluxes. J1 is the heat flux, and J2 is the mass flux. So, according to the linear theory, you remember, is the figure on the bottom of this picture, called the neoclassical theory. Fluxes and forces are linked by Onsager matrix, where the diagonal element are the dimensionless electronic conductivity in case of electrons, and the dimensionless thermal conductivity. The non-diagonal components are the thermoelectrical coefficients. So, our aim is to compute the expression indicated here by JE1 is the losses. I have to perform this operation. J1 means losses of mass, J3 means electronic losses, energy electronic losses. For this, we have to compute these two quantities, the forces x1 and x2. J1 and J2 are known because are given by these expressions, as J1 and J2 are directly linked to the pressure gradient and thermal gradient. So we know the fluxes. Our task is to obtain x1 and x2 if we know J1 and J2. We put the value here and we compute this expression. If we do perform these calculations by using only the Onsager matrix, we mean fluxes and forces are linearly connected each with other throughout the Onsager matrix, we obtain the curves indicated here on the bottom of the curves. However, when plasma is out of equilibrium, we have to know what is the relation between J and X in order to obtain X. This is the scope, the aim of this theory. For this, in previous work, we have shown that the transport coefficients are given in the case of a system subject to only two thermodynamic forces, are given by this expression. G mu nu is proportional to the Onsager matrix times what we call a conformal factor, where the exponent should satisfy this equation. This theory, the demonstration of this equation, of these results, can be found in Chaos, published in 2020, and I shall not show this here. But let's assume for the moment that phi should satisfy this equation, and if we know this solution, we can know the transport coefficients, and then by reversing this expression I can find x, and then from these two equations I can find the losses and compare the results with experimental data. To solve this equation, we have to set up the boundary conditions. For this, we distinguish two cases: plasma in collisional regimes and plasma in turbulent regimes. Let's start with the first case, plasma in collisional regimes. But in this case, we impose that at the axis x1, x2, we impose the validity of the Fick law, this axis, x1 axis, and the Fourier law. And we impose that for large value of the thermodynamic forces, there is no privileged direction. We mean that for large value of the thermodynamic forces, phi should be a constant. This reflects the physical assumption that there is no privileged direction. Okay, if we solve this equation, and as I said, if we know phi, we know g. By knowing g, we can invert this equation because we know j, we know x, and then if we know x, we can put these results here and then found these two losses. Okay, if we perform this calculation, we obtain these graphics. As you can see, the agreement between experimental data and theory is quite good in the first part, in the collision regimes, and not good at all towards the boundary. And this because the turbulent regimes dominates the collisional regimes. You can see that in the first part, where the collisional regimes is dominating, in this case the entropy production sigma of the collisional part of the entropy production very high, and the second region, turbulent regime, the collisional part of the entropy production is very low, because the entropy production is mainly due to turbulence, the big contribution due to turbulence. Okay, so now we have to solve the problem in a turbulence regime. As before, we have to establish the correct boundary conditions, because this equation for phi remains the same. But we say that the phi, the conformal factor phi, is constant for very large value. But we impose that in the turbulent regime, phi for very large distance is another constant. But the peculiarity here is that here along the axis, the Onsager law are not valid, because turbulence destroyed the validity of the Onsager law when plasma is far from equilibrium. We know that the Onsager theory is valid close to thermodynamic equilibrium. In this case, we assume that the transport coefficient remains constant at very large value of the thermodynamic forces, but the Onsager law are no longer valid. Fick law and Fourier law are no longer valid. These equations, solve this equation is not easy because we can see the equation is highly nonlinear. But we can make an assumption. We make the assumption that the transport coefficients have the same intensity regardless of the direction in the space of thermodynamic forces. I mean, the transport coefficient depends only on this distance to the origin of the axis, I mean thermodynamic equilibrium, but not on the angle. But this means that this quantity, which we call sigma L, is the quantity that is linked after transformation of coordinates, is exactly equal to the distance to the equilibrium. Then, to say that the transport coefficient have the same intensity independently of the direction in the space of thermodynamic forces is equivalent to saying that when the F2 plasma is in turbulent regime, the transport coefficient depends only on sigma L. If we make this hypothesis, which is written here, we assume the possibility A, assumption A, strong hypothesis. In this case, we obtain the solution. We can find the solution of the nonlinear equation, which is given here. Of course, this equation should be combined with the closure equation, linked J with the thermodynamic forces. And in terms of a scaled variable y, we obtain this equation. Now we have just to solve this algebraic equation. If the variable is y is the sigma L, our variable scaled. This means that we have to solve these equations. I mean, we have to find the coordinates of these black points. This parabola, similar to parabola, but it's not a parabola because it is a y times 1 minus log y, is given by this continuum line. And these horizontal lines are the right-hand side of this equation. These points are the solutions. So the solution give us the value of sigma L. If we know sigma L, we can find the entropy production, is this one. And finally, if we perform, all calculation I showed you before, so if we know sigma L, we know X and then the losses, we obtain these graphics. This is the second part of the graphics, the black continuous line, is the theoretical solution in turbulent regime. I repeat, why turbulent? Because the turbulence destroyed the validity of Onsager theory. And it says that the plasma is so perturbed that there is no privileged direction. As you can see, the agreement between theory and experimental data are the dot lines, are quite good, both theoretically and both quantitatively and qualitatively. Indeed, in the first two cases, the curves in Onsager theory is upwardly directed, while experimental data are downwardly directed. But this is exactly what we obtain from the theory developed and proposed by us. Conclusions. Let me say that in previous work we have derived the nonlinear equations that have to be satisfied by transport coefficient for system out of the non-Sarger region. We applied this theory and these equations to the particular case of Tokamak-plasma, plasma confined in tokamak. To test the validity of the theory, we consider the concrete case of a plasma confined in Frascati tokamak upgrade, which is subject to only two thermodynamic forces, temperature gradient and pressure gradient. Additionally, plasma is subject to a very strong toroidal magnetic fields, which limit strongly the intensity of turbulence. This gave us the possibility to solve the equation for this particular tokamak, and we found that the theoretical results are in fairly agreement, for the first time in fairly agreement with experimental data. We now the objective is to apply these equations to more complex tokamak and reactor like ITER, and why not the Diverto tokamak test facility. And the final scope, is to find finally a theoretical framework where predictions are in perfect agreement, very good agreement, I would say, with experimental data, in order to foresee the experimental results as expected by us. Thank you for your attention.